All right, so we have chain rule for trig functions now. And then therefore the use substitution with trig functions. So remember, our basic way of doing this use substitution is based off of realizing that we're taking the integral of something that was the answer from a chain rule. We have an outside function, we have an inside function, and then we have the derivative of that inside function. And so if we make this basic substitution that u equals g, and du is the derivative of u, which should be the derivative of g, and we swap that out, we're essentially just looking at the integral of f of u du. And so all we have to do really is with these three functions that are sitting here, we're really only going to integrate one of them. And the one we're going to integrate is f. We're going to find the antiderivative of f. But we're going to do this as it relates to now trigonometric functions. So let's look at this. The derivative of 5x is 5. So if I say u equals 5x, du would be 5 dx. So we take this and this, bring that out, that's our du. Take this out, that's our u. What are we left with? The integral of cosine u du. And so the integral of cosine u du is sine u plus c, but u was 5x. Replace that u with a 5x, and we have our answer. Okay? How about this next one? Well, you would have to recognize that the derivative of tan x plus 3 is secant squared. And that's the whole thing with substitution, right? Is a pattern of recognizing that you have a function and that function's derivative within your integrand. So if u equals tan x plus 3, then du equals secant squared x dx, and this integral simply becomes u du. This is a du, this is u. So you get u du. So the integral of u du is u squared over 2 plus c. Using power rule, just a power rule, u to the first power. Replace your u with what you called u, in this case tan x plus 3, and you get tan x plus 3 squared over 2 plus c as your final answer. Here's another very common one. One thing we know a lot about use substitution is it doesn't always work out perfectly. Sometimes we're off by a constant multiple, but we can always make that work. So recognizing that the derivative of cosine is sine, this is my power on the outside. So if I don't let u equal cosine squared, but I let u equal cosine x, okay, then du, which is the derivative of cosine x, is minus sine x dx. Now the problem is I don't have that extra negative. There are a couple ways we can handle it, but the way we've been talking about it is we should move this negative to the other side of the equation. So now it's a plus, so move it with my du, and then therefore what do we have? What we have here is that we get the integral of u squared, and then we have a negative du, so that's now the integral we're going to do. Well, it's just a power rule with the negative being basically a constant multiple, so we have negative. The power rule would be u cubed over 3 plus c. Replace your u, which was cosine, in, so you get cosine x cubed over 3 plus c. Now you can write it that way. Sometimes you see the 3 written inside the function like that. Third x over 3 plus c. Whether you write it this way or this way, it's the same thing. You should know your trigonometric notation by this point. And that's it. Okay, so recognizing again a function and that function's derivative. Like a couple other options you could have done here would that you let u equal sine x. The problem with that would have been that the derivative is cosine x dx. But you don't have just a cosine x, you have a cosine squared, so that's not going to work. Another option is that u could have been cosine squared x. The problem there is that the derivative for that's even more complicated. That's a chain rule problem. You do the outside first, which is the power, and then you have to multiply by the derivative of the inside function. Now that's your du. Well, that's again too much for what we have, so that doesn't work. So the only way that we could get this integral done with this substitution is through this particular one, letting u be cosine and du being, in this case, negative sine x. Even missing the negative, we could still make this work though. But this would not. Here's a couple more. This one's very closely related to the last one, but I got a little bit more happening here because now there's a 3x and a 3x. I also swapped out my sines and cosines the other way. So we use the same tactic. We're going to let u equal, in this case, sine, but it's now sine 3x. So just make sure you find the derivative correctly. In this case, the derivative, we would really have to use the chain rule. This is the inside function. This is the outside function. We would have cosine 3x times the derivative of the inside is 3 dx. Now, we have cosine 3x dx sitting here for our du, but not that extra 3. So I'll just swap that to the other side by dividing, and therefore what do we get? We get 1/3 the integral of u squared du. Okay? This is du over 3, so there's the du and there's the over 3, and this right here is u squared. So then once you break it down to that, it's a very simple integral. The only thing you have to integrate out of this whole thing is really just the power component to it. So I have this 1/3 as a constant multiple. I end up with u cubed over 3 plus c. U being sine, and this will give me 9. So what do I get? I get sine cubed 3x over 9 plus c. Again, here's where it helps to know your basic derivative rules. You need to know that the derivative of cotangent x is negative cosecant squared x. If you know that, this is very easy. You see u and a du sitting right here. Now again, we're off by a negative, but we can swap that to the other side here. Okay? And we would end up with negative integral of du over u. And again, you would have to know, well, what's that the integral of? Well, we should know that that is your basic setup for a logarithm. Du is the derivative of u. This is like saying u prime over u. That's our derivative rule for log. So then the answer for this would be minus log of u plus c. In which case we have minus log of u being cotangent x plus c. And what's going to happen is this is going to then start leading us into how we get the integral of the other basic trigonometric functions. Now that we have u substitution and we know some of these other basic integrals like log and power rules, etc., we can get into the other 4 trigonometric functions that we haven't done yet. So here you go. We've done this one. We've done this one, but I've pointed out that these 4, we have not actually come up with the integrals for tangent by itself, secant by itself, cotangent, cosecant by themselves. We've done the integral of secant squared, but not just secant. So here we go. Now we're ready to finally do this. So let's look at one at a time. Let's look at tangent, okay? Now here's the answer. Okay, there's the answer. That's what it is. And really, you're just going to need to commit that to memory. Would be the most beneficial thing to do. But let's see where it comes from. Well, it comes from some trig identities and u substitution. So if we look at this one, if I rewrite tangent as sine x over cosine x, that's a basic trigonometric identity. It's called a quotient identity for tangent. And I say, let's let u equal cosine x. Then the derivative would be minus sine x dx. Well, I have the sine x dx. I don't have the minus, so I'll swap that to the other side. And what do I end up with? What I end up with is negative integral of du over u. Here's du with an extra negative. That's here and here. And here's u. Now remember, du over u, that's the derivative of u divided by u. That's u prime over u. That's your basic rule for logarithms. So we're going to get negative log of u plus c. Well, what is U was cosine x. So there you go. That's where it comes from. Now you can just do that every time you have to do the integral of tangent, but I think you would benefit from committing this one to memory. Another way you could write this answer is to take this negative, use your log properties, take this negative and write it in as a power, right? Powers inside could come out as multiples and then vice versa. So I could write this as log of cosine, log of cosine to the -1. Now that's not inverse, so that's a problem. We usually wouldn't write that. But anything to the -1 power is reciprocal. So we never would really write the answer that way, but the reciprocal of cosine is secant, so you might see the answer written like this instead. They're the same answer written two different ways. Which one you see more often kind of depends on, the teacher and the textbook. For us, this one will be the one you'll see more often, but understanding that they're, one and the same is pretty important. Let's see another one. So secant x. How do we get the answer for secant x? So we saw what the answer was, but how does it come about? Well, this one's a little more challenging, but once you see it done, you should understand why it works. So we're basically going to try and get a UDU for this integral, but we don't have much to work with. So what I'm going to do is I'm going to introduce more to this problem than is there. So I have secant x, and then what I'm going to do is I'm going to multiply by a fraction that is equal to 1. So the numerator and denominator will have to be the same. So what it's going to be is it's going to be secant x plus tan x over secant x plus tan x dx. So it's still the same integral because remember, this is just 1. But how does that help me? Well, this secant would distribute into this numerator, and I would end up with secant squared x plus secant x tan x over secant x plus tan x dx. And so here you see it happening, hopefully. U will be secant x plus tan x. Sorry, I keep hitting that. Tan x. Du would be the derivative. Now, since these are added together, I could do this one separate from this one. Derivative of secant is secant x tan x. Derivative of tangent is secant squared x. So secant x tan x plus secant squared, well, that's exactly what's sitting right here. So here's your du. Okay? So we have du over u. That's ultimately what this boils down to. Du over u, which is that logarithm again. So we should have log of u being what? This, secant x plus tan x, and then throw a plus c on there. So there's your answer. That's the integral of secant. Again, you could do that every time you have to take the integral of secant. I highly suggest you commit this to memory. It's one of your most basic functions in trigonometry. You should know how to do the integral. So you should know how to do the integral of secant squared. You should know how to do the integral of secant x times tan x. And you should know how to do the integral of just secant x itself. So again, just to review the basic integration that we should know the integral of sine is equal to negative cosine. Integral of cosine is equal to sine. Integral of tan is equal to negative log of cosine u. Integral of secant is equal to the log of secant u plus tan u. Now, cotangent and cosecant, I didn't do them, and I'm not going to, because they basically come about the same way. How do we do cotangent? Basically the same way we did tangent. We did tangent by writing tangent as sine over cosine. We'll do cotangent by writing it as cosine over sine and kind of switching our u and our du. And you see that's why we get the answer of log sine u instead of log cosine u. And the same thing goes with the cosecant. Same sort of tactic I took with secant. I multiplied by secant u plus tan u. Here I'll multiply by cosecant u plus cotangent u, and you see why we get the answer the same. But without even seeing these done, you're going to need to know these and commit these to memory for when we do need them. Then we have these other ones that we've already talked about well before this, because these are just based off of your simple derivative rules. The integral of secant squared equals tan x. The integral of secant x plus tan x equals secant x. Integral of cosecant x, cosecant squared x equals negative cotangent. And finally, the integral of cosecant x cotangent x equals negative cosecant x. So these are all the trigonometric integrals you should have down. And I highly, highly suggest you start committing these to memory as soon as possible. It will benefit you greatly. All right, so let's look at this one. This is not cotangent x, it's cotangent 2x. So what are we going to do? We're actually going to use substitution here. I'm going to say u equals 2x. du is the derivative, which would just be 2 dx. Now we don't have an extra 2, but again, that should be fine. We'll swap it to the other side. So what do we end up with? We end up with 1/2 integral cotan u du. Okay? Again, the dx is du over 2. And here's the du, and here's the over 2. And this 2x is your u, so there you go. But in order to do this, you would have to know what the integral of cotan u is, which we just talked about. And so I would get the log of the sine of u plus c. That's the integral of cotangent. Replace my u, and I'm done. So 1/2 log of sine of 2x plus c. And here's another one. I can take the integral of the 2 separate from the cosecant because of the minus. So I could do the integral of 2 dx minus the integral of cosecant 5x dx. But in order to do the integral of cosecant 5x dx, I really should use a quick little substitution. U equals 5x, du equals 5 dx. Divide the 5 over because I don't actually have an extra 5 sitting anywhere in here. Okay? And so what do I get? Well, the integral of 2 dx by itself is going to be 2x. Minus, then I have the integral of cosecant u du over 5, so I'll pull out the 1/5 into the front. Again, if I know the integral of cosecant u, this is easy, and I should get to know what that is. So I'll have minus 1/5 times the integral of cosecant u is negative log of cosecant u plus cotangent u plus c. Okay? Let's fix some of that up. It's kind of messy. There you go. Replace your u. Your u is 5x, so I'll replace my u here and here. And what do I get? I get 2x minus, or plus actually, because this negative will give me plus 1/5 log of cosecant 5x plus cotangent 5x plus c.